Session 1 will explore some of the key questions and debates in the embodied carbon discussion. There are 4 presentations in this session. Each will be presented for about 15 to 17 minutes, followed by a 5-minute question and answer. Please share your questions with us again through Q&A feature of the Zoom. The first speaker in this session is Dr. Alice Moncaster, Senior Lecturer of Engineering at the Open University, who will present her research entitled A Manifesto for Minimal Embodied Carbon, a Question of Politics, Not Percentage. Alice, floor is yours.
Thank you very much, Raman. I'll just try sharing my screen. Oh, you've disabled participant screen sharing.
Oh, I'm sorry. So let me make you co-host. And now you must be able to share your screen. And
Thank you.
I'm going to pin you as well. Okay.
Okay. Is that all working?
We're not seeing your screen.
My apologies.
I think it is working now.
Okay. So in fact, that's my slide 2. So let's try starting on slide 1. Thank you very much for the invitation and the introduction, Raman, and thank you, Luke, for setting this problem up so brilliantly, because my presentation doesn't really include any of the numbers, all the percentages about embodied carbon. And Luke, you've done an amazing job at presenting the whole problem to us. Mine is a bit more kind of esoteric. I want to take everyone out of thinking about the actual numbers and think where they come from and who is talking about them. So let me just get my mouse. So briefly, I'm going to cover percentages, politics, a little case study, what this means, and some conclusions, and then propose an embryo manifesto, which is by no means finished. So first, how are percentages used? Well, of course, we all know about percentages, and certainly they're used to inform. And this is a graph I just downloaded from the UK Office for National Statistics, which is quite worrying. It shows us that inflation in the UK at the moment is 10%. This is a graph of inflation, and it shows that it is way higher than it has been for very many years, when it was hovering between 0 and 2.5%. But the same Office for National Statistics also offers us this graph, which shows exactly the same figures, of course, but going all the way back.
Alice, sorry to interrupt you. We are not seeing you in full screen. We are seeing your notes as well.
Oh dear, are you? Right, let me try. Perhaps okay. I need to new share. So can you see exactly the same now?
If you go to the full screen now.
Yeah.
We still see your notes. And I'm not sure how we could...
I think, Alice, sorry for interrupting. If you have 2 screens, I think you need to share the other screen with us.
Okay, so if I stop share, if I share desktop 1, can you now just see my slides?
Yes, that works great. Thank you for the suggestion.
Thank you. That's yes, I do apologize. We're not allowed to use Zoom at the Open University in the UK for some reason, so I'm a bit of a novice on using it. Okay, so percentages. So we had got to this second chart from the UK Office for National Statistics, which shows inflation going back to 1989. And I'm putting this up to say, obviously it's the same data, but it gives you a different impression. And if you were around in 1989, 1990, it might make you feel quite scared because you might remember, negative things that happened back then, or it might make you feel more confident because you'll think, well, we've been through here before and we can come out of it again. So percentages, how they are presented affects the message. Percentages are, of course, always also used to persuade. So this is a recent example from Black Friday, which I'm sure we've all seen. Excuse me. And of course, there's been a lot of academic research which has looked at the power of numbers to persuade, in particular in fields such as economics and management and policy studies. And this is a book written by Theodore Porter called Trust in Numbers, who demonstrated that the political use of measurement stems from a desire by the state to impose control through encouraging trust. And particularly, I wanted to pick up the fact that he says that the state uses public trust in professional experts to legitimate contentious policies and decisions. This is by Professor David Mackay, who was a professor of physics at Cambridge and chief scientific officer. So he was actually a physicist, and he said that numbers can be deliberately chosen to create a false impression. And finally, I wanted to pick out this one by Martello and Jasnov, who are sociologists, who went further, and they said actually how we represent environmental problems is linked to the ways in which we choose to solve them. And really what they were saying is the numbers that we choose to use are based on what answer we want them to show. So I would argue that it's not just numbers. Percentages are particularly easy to use to present your chosen argument because they are always relative to something else. So the choice of which numbers you can include or exclude can be made on both sides of that equation. So the other concept I wanted to talk about is politics. And the classic definition of politics is a power struggle about who gets what. It's a contest over the distribution of material goods. But there are two challenges to this classic definition. And the first is that it's also about values and lifestyles. So it's about things such as the environment and how important that is. And then the second challenge is the ideational turn, it's called, which says it's also about how issues are framed and who controls the narrative. So who decides to say what is important and what we're going to talk about. So how does all this relate to embodied carbon? I'm going to use a historic case study of UK policy from 2003 to 2010, but I can assure you that this is going on all the time, all over the world, right up to the present day, and will continue to. So back in 2010, a low carbon construction report from the UK government said that as soon as sufficiently rigorous assessment is in place, the government should require the conduction of a whole life embodied plus operational carbon appraisal for construction projects, and that industry should agree with government a standard method of measuring embodied carbon for use as a design tool. So those of us working in the UK at the moment know that this is going on at the moment. It still hasn't been regulated. We are still doing this. So what's taken so long? This was 12 years ago. So what was going on back then? So just as now, there were policy drivers to reduce energy use and carbon emissions, and they were from energy security. There were real worries about the availability of fossil fuels, just as there are now, and from climate change. And of course, we all knew about climate change since 1987, when the World Commission on Environment and Development report, Our Common Future, stated that climate change must be considered a plausible and serious probability. So climate change was not new, but there was also the added pressures to encourage economic growth, keep the construction industry buoyant in order to increase economic growth, and in particular to build more houses. And so this was a contest going on, a political contest, if you like. So these are some of the major reports that came out during that period. And the first couple, 2003 Sustainable Communities Plan, but it basically stated we need a lot more houses. And then the UK government employed Kate Barker, who was an economist, to review the housing supply. And she concluded that we needed 150,000 new homes per year. And of course, she didn't mention energy or greenhouse gases at all. She just mentioned economy, because that was what it was about. After that, we started to see evidence of this political contest going on. So there was a consultation at the end of 2006 on building a greener future towards zero carbon development. So this was a policy also about building homes, but it was about building zero carbon homes. And what the consultation was asking was, what is the definition of zero carbon? So it put forward its definition of zero carbon and asked for comments. And the industry comments were numerous, And a lot of them said it should include embodied energy. So these were people from industry, these were designers and contractors saying it should include embodied energy, embodied carbon. And the report on this consultation brought these out in both the conclusion section and the section which showed the recurring and significant themes throughout the consultation. So this was being talked about and pushed really by industry back then. However, a month after that consultation was published, the actual policy statement came out and it completely dismissed it. And it said, we don't believe a full consideration of embodied carbon is practical or realistic in the short to medium term. They in fact changed it into, they put it in a section which was about white goods, about services goods. And they've said, therefore, that there isn't enough evidence and we don't know how to do it. So the fact is, they dismissed it, but they did know the impact of construction materials. We'd had the BRE Green Guide specification giving us an idea of what they were for the last 10 years at this point, and the Bath Inventory of Carbon and Energy, which many people around the world have used since, was first published in 2006. And in fact, even the UK government had produced a previous report from a different government department saying that carbon emissions from the production and transport of construction materials were really important. And they came up with these figures: 44% of all construction-related emissions and 72% of a building's life cycle carbon is embedded into the physical asset. So here we see embodied impacts were seen as really significant by some parts of the government, and we see the use of percentages in particular being used to persuade of a political argument. And percentages are, of course, used and always have been used to discuss embodied carbon. So it's often said that embodied impacts make up less than 10% of whole life impacts. And someone said that to me about a week ago, which I was quite surprised at. That even the low carbon construction report, that one in 2010 that said we should measure it, only came up with 16% of the total carbon footprint being due to manufacture, distribution and operations on site. And a paper from 2002, which looked at UK construction, Johannes and Norton, said the energy initially embodied in a building could be as much as 67% of its operational energy, although they only used a 25-year lifetime, which I thought was really interesting. So that shows too how figures on both sides of that percentage equation can be chosen to demonstrate what you want to demonstrate. I think they wanted to demonstrate that embodied carbon was important and a big figure. So the definition of zero carbon had been set by the DCLG, the government department who'd won control over the narrative and decided that zero carbon, how zero carbon would be framed. This was their final report. The Calcutt review came out in November 2007, who said, and John Calcutt was a house builder, basically. He said, our review shows clearly that the house building industry do have the potential to deliver, it's now gone up to 240,000 new homes a year by 2016, and to achieve the zero carbon target. So if you make zero carbon only include operational carbon, then it's quite possible to build and to achieve zero carbon. And the strategy for sustainable construction in 2008 only mentioned embodied carbon once, and it said it's generally far less than energy consumed during the lifetime of the building or the infrastructure project. And it also said, nevertheless, is already addressed. Basically, someone else is doing something about it. So arguments were being made that embodied carbon is minimal, that it's already been addressed elsewhere, and it's too complicated to calculate anyway. So this is real dismissal. And these messages are continuing. These arguments about embodied carbon are happening, as I was saying earlier, around the world. This is a conference paper that I wrote with my colleague Tove Malmqvist back in 2020, and this is looking at the last 10 years in the UK and Sweden, and how these political arguments have been happening through both our countries since then, quite differently, but each of them with some elements of the same things happening. And this fed into our report for the International Energy Agency, EBC Annex 72. And also more recently, we've looked at this in a new paper in Embodied Carbon of Concrete in Buildings, in Buildings and Cities. So we've started to look at the political aims and uses of percentages of the big trade sectors, who are those who are meant to be already measuring and reducing their embodied impacts back in 2008, according to the DCLG. And we scrutinised the calculations behind the percentage figures being claimed and disputed them. However, the point is that these percentage figures are taken up and reported and repeated by others. So this was the National Engineering Policy Centre and Royal Academy of Engineering in the UK, who repeated the claim of the cement and concrete industry that they have already delivered a 53% reduction in absolute CO2 emissions since 1990. So, embodied impacts were excluded from the metric of zero carbon, even though it had been discussed and calculated within both academia and industry for many years. And in particular, the evidence of the dissenting voices, those ones that report from DEFRA and the industry consultation on building a greener Britain, are indications that this was a political struggle. This was a definite political move to keep it out. And as Theodore Porter also noticed, professional industry experts were being used throughout to evoke public trust. And throughout, there were those industry experts leading the government reports. So I wanted to look briefly at political theory, which says that industry networks and lobbies act along this continuum. So at one end, there are the special interest groups who are self-organised individuals from that industry. They fight for their own collective concerns, and they have high autonomy, but they have low political power relatively. And at the other end, there are what are known as policy networks, whose membership and topics, and in fact the very setting up, is defined by government. They have low autonomy because really the government is controlling what they're talking about and even what they're deciding. But their prestige gives them power within industry. And so they've almost swapped, in this case, their right to autonomy for being part of this more elite policy community. And so at this extreme, power is retained by government acting through the perceived expert influence of the industry groups. And of course, they also choose industry members who really actually agree with what they're looking at. So they choose house builders to demonstrate that they need to build more houses, for example. And throughout this, numbers, and I would say in particular percentages, are used as part of the political process to persuade and to cause effects which would not otherwise have been. And the history also showed the choice of which numbers to include can determine the outcome. And this is what Porter said: quantification is not merely a strategy for describing the social and natural worlds, but a means of reconfiguring them, not just describing them, but reconfiguring them. It entails the imposition of new meanings and disappearance of old ones. So I think everyone at this symposium will know that embodied impacts are not minimal. And we have heard from Luke to see just how high they are and how important they are. We know they're not now too complicated to assess. And we also know that they're not necessarily being addressed, particularly by the trade sectors that were said to. I've tried to show how politics and numbers are deliberately used to frame narratives, while in particular percentages are used to support the answer that is wanted. And in particular, I've shown that in the political battle over competing aims to reduce climate change or increase construction, the increase of construction has won through deliberately downplaying and excluding embodied impacts from the definition of zero carbon. And we are still fighting the results of this now, and still trying to impose it, include it in regulation. So are we still playing the losing game, is my question. My concern is that we are still playing this game set out by the political interests who are focused on maintaining economic growth at the cost of the climate and through continuing essentially business as usual and for as long as possible. So my embryo manifesto is, first, we should accept responsibility for the size of embodied impacts, and we should accept that these are happening now, not in the future, and they need to be decreased radically now, not in the future. And so we need to do that. We need to ask first, do we need to build anything at all, or is there an alternative? And next, do we need to build like we are doing, or is there an alternative? And finally, to always remember to question the numbers and percentages that we are being given and ask cui bono, which is who gains. Thank you very much. I think I had a thank you for listening.
Thank you very much, Alice, for sharing your work. We have only 1 minute or so for questions. If there is any question, please share with us. I could ask a question, Alice. So the ideas of, I think the core of your the presentation was about perhaps building less would help us in addressing some of the climatic issues. But my question is that how do you think, what cultural, what social changes we need to make in our society in order to address the climatic issues related to construction, do you think?
That's a very political question. So I think it depends which part of the world you're in. I think if you're in the UK or in the States, what we need is more equal sharing of the construction, the built environment that we already have. I think there are other parts of the world where, of course, more construction is still needed to provide shelter and warmth and essential services for the people who live there.
Very good.
Brief answer for you.
Thank you, Alice. I'm reading here a question. It says, thank you very much for this interesting talk, Dr. Moncaster. I'm a huge fan of your research. I have followed your studies for a while. I completely agree with what you've laid out in your talk just now. Would you like to hear your thoughts on the practical solution to reduce the embodied carbon? The British economist Dieter Helm proposed the idea reducing our own carbon consumption is the first step. Helm argues that we, the ultimate polluters, should pay based on how much carbon the products we buy produce. What do you think about this idea?
So this is the idea that we pay for the carbon. I think it has some traction. I think the trouble is that rich people end up still emitting as much carbon as they would because they can still afford to. And yeah, I'm concerned that it doesn't necessarily add up. But thank you very much, Ming. That's a great question. And I'll look up Dieter Helm.
Okay. Thank you, Ming, for the question. And thank you, Alice, for sharing your research. Our next speaker in this session is Dr. Guillaume Hebert, Associate Professor of Sustainable Construction at ETH Zurich, presenting a work entitled Climate Neutral and Circular Built Environment, right here, right now. Dr. Hebert, floor is yours. And I'm going to make you co-host. So
I hope you hear me now.
We can hear you well.
Yep. Cool. Great. Now I try to share my screen and then we see. Up. Let's try. Whoops. Share. Maybe like this could work.
Yes, it works very well. And I'm going to pin you as well.
Just remove that. Okay. Okay, then, I mean, thank you. Thank you very much for the invitation. Thank you, Raman, for organizing such a, and Alice for organizing such a great event. And I will present our work on how we see climate neutral and circular built environment. It's mainly, I would say, let's say Swiss or European perspective on the climate neutral and circular buildings. And I really think. I mean, this is a known studies, and I guess everyone here in the room knows the idea of why we need to focus on embodied carbon is basically, if you see, we have made quite a few progress on how to operate the building. But if you look at the average embodied emission, basically it's always more or less always the same. Yeah, this also, you know, that we have to reduce the emissions drastically, so there's not much time to lose. And maybe just to come back to some, well, I think it's kind of in line also with what Alice was saying on the The idea is that we knew that, but we have lost a lot of time to model blurry the water or something like this. This is the work, because when we say, okay, embodied carbon, we have to reduce, then it's like, okay, let's move to wood and build everything with timber. And this is a great work from Francesco Pomponi and his team. I think they will speak afterwards, where they showed this supply demand, how much forest we have, how much buildings we need to build, and to show that most of the place where we need to build, which is mainly Southeast Asia, Africa, and South America, we just don't have enough timber, except if we agree to cut the beautiful tropical forest that we would like to preserve. The other way of doing it is to say, well, we can keep the business as usual. We do concrete, except that we do carbon capture and storage, and so we continue to produce cement, but without CO2 emissions. That's magic. This is a study from the Carbon Capture and Storage Institute, which shows, and I was surprised to see it. It's like it's 2021. They clearly show that, okay, to get to from 2020 to 2050. We just have to multiply by 140 the storage capacity, which is quite surprising, because in the same report they show that the carbon storage capacity has actually been reduced by 30% in the last 10 years. So it means in the last 10 years you have reduced the capacity by 30%, and we think that we can increase it in the next 30 years by 14,000%. Well, I mean, the pace doesn't work, but the problem is, like, if it doesn't work, then we will end up at a moment where we have emitted too much CO2. And this is the scale-up possibility, and this is another paper from the carbon capture and storage. Problem is also there's an acceptance. I mean, all this, there's the technology, there's the cost, and then you have to put pipelines, you have to put storage. Who will accept to have a carbon capture and storage plant under their house? So it's clearly a huge gamble on the future. And what I would like, and I think that's also what somehow Luc proposed, is that there are simple solutions. There are simple solutions. It's just that we have to see the problem differently. The problem is relatively easy, as you have carbon that is, let's say, flowing across the Earth. This is the full carbon cycle of the Earth. And so you have huge flows, and I think we can typically play with these flows to make it climate neutral. The way to do it is maybe first to simplify a little bit. You have three main flows. One is the human flows. That's the one, like 6 gigaton carbon per year, more or less, 6-9, something like this. And it's purely linear. That's why it's very small, but purely linear. That's why it creates climate change. And then you have two huge circular flows, which are the biological carbon cycle, 120 gigaton carbon per year, and the geological carbon, so the equilibrium between the ocean and the atmosphere, which is 90 gigaton carbon per year. They have a certain pace, these flows, because if you think spring, winter, you have a carbon molecule that is going in spring, stored in the leaves, and then falling, so being released in the atmosphere. And then on the other side, for the geological cycle, it takes much more time to go through the ocean, deep ocean, and then come back. So how do we play with that? The last linear flow that we have to think about is also the material. A linear flow of material of around 70 gigaton material per year that is extracted, and also landfills. And so first one is to say, okay, can we reduce these flows? This is, again, something that I think is extreme. I mean, that's more or less what I think what you said, Alice, is like, it's easy, it's known, and there are solutions. This is a study we did, a review that we did 2 years ago, to show that if you look at the cement industry, and if you don't look just at the cement as an industry, as a industrial plant, but that you look at the cement as a complex value chain of various different actors, from the waste producers that can produce alternative fuel to the cement, to the concrete producers that can adapt the amount of sand, gravel, and cement in the concrete, to the architect or the engineer that can design the building, the demolition company that can either put everything in the dump site or actually sort the things or even deconstruct, and to finally the client that can act or not. You have savings that are very easy to do, which means keeping the standards as existing, keeping the technology as existing, and you can save, if you see here, something like 60%, let's say 50%. So you have like 50% of CO2 emissions that can be saved just by doing well our job, meaning less clinker in the cement, less cement in concrete, less concrete in structure, less structure, and a certain reuse of the final of the waste. And that's it. So you have already saved 50%, which is great with this mainly new type of cement, is that they will carbonate faster. So it means usually the cement, if you know a bit of the cement chemistry, you have limestone that you burn. So you have CO2, fossil CO2 that is released in the atmosphere, but within a certain geological time, the cement will go back to limestone, and so you will recarbonate your cement. This takes 1,000, 10,000 years. So the thing with this new cement is that they will speed up this geological cycle, which you see here in this diagram. If you take the CO2 emissions, this is in blue for the production, and here is the carbonation rate, so the speed at which you recapture the CO2. And if you see, you divide by 2, and the carbonation rate you more or less multiply by 3, which is still not big. It's like 18 millimeters in 20 years, but it's not that bad, especially if you think about structure that would carbonate as fast as possible. So typically structure where you would have as much as possible surface exposed in order to carbonate as fast as possible the remaining volume, which could be one solution like this. Typically, well, I think that could be an interest of a 3D printing, where you would expose as much as possible the concrete to carbonate faster. So on one side, you're emitting less CO2, you're recapturing faster your CO2, and on the other side, you can obviously use or play with this biological cycle, which is what Luke was saying with this hempcrete or things like this, where what you do is, on the contrary, slowing down a relatively fast biological cycle. Usually hemp or straw would absorb CO2 and be released after 1 year. You put it in the built environment and you store it for 50 years. So you will actually use the biological cycle as a pump to extract CO2 and not do a complex carbon capture and storage. And so you can capture relatively fast CO2, especially if you use fast-growing bio-based material. For insulation and for European perspective, straw, hemp are clear alternatives. Here it's a few examples just to show that it's not a crazy building. This is a very normal building in Paris. It's a hempcrete on the facade. Here it's a building that you don't see too much, but it's a straw bay with an earth plaster here in Geneva. The great thing with this is also that you can regulate the indoor moisture. So you improve the environment, you also improve the indoor quality. And so to kind of conclude on this logic, what I really think is that we should not think about one solution like carbon capture and storage, or let's say timber. I mean, timber is part of the solution, but like one solution that will save us all. It's really the idea of saying, how do we put the right material at the right place, and typically the right amount of material within a certain building? And the way we could present it is to say we just need to change our material diet. The same as it is obvious, I think now for most of us, that a vegetarian diet is better for your health, is also better for the environment. Doesn't mean that you should not eat meat, but at least if you reduce the amount of meat that you eat, it's better. And here it's a bit the same. It's like, it's good to have glasses and windows in your building, but you need to say that this is a super carbon intensive material, so you need to use as less as possible. On the contrary, you have to optimize your low carbon material like concrete, glue laminated timber, bamboo, etc. And you have to use as much as possible vegetable, basically, so carbon negative material being straw, hemp, solid wood, and others. And of course, carbon neutral like earth. And then at the end, you have a building where you have a balance between your carbon intensive and your carbon negative, and the building itself is climate neutral. And it can be fancy. This is like the fancy example, but I think it's as to show that it also allows a huge diversity of architecture, which can be very exciting. And finally, just the question before the answer before you raise the question, do we have enough? This is a study that we did recently to look at it's very basic, but how much bamboo and how much straw you have in global south. I mean, straw in global north for the renovation of the existing building stock, bamboo in global south for the construction of the new building stock, and how much demand you have. And you see that most of the time we have much more supply than demand. So we have enough materials. And to finalize, because this was to say, okay, it is possible to be climate neutral. The last thing is, can you be circular? And for that, the circularity is a very, I think, complex question we can discuss, but to make it brief, if we just think circular in terms of amount of material, then I think there's a certain confusion, because the main material that is extracted from our cities is not, let's say, glass, windows, and things like this. It is excavation materials. If you see here, this is the material flow in Switzerland, where you have the construction and demolition waste, which most of the time is actually already circular with recycled concrete. And the thing that is absolutely not circularized is the excavation material that goes to landfill. And excavation material is actually earth. So if we want to circularize our construction, we should think on how do we use this excavation material. Here, a few examples of nice buildings. Here it's in Geneva, from a startup in Geneva called TerraBlock, where they do compressed earth brick. I mean, it's a very classic technique, but they renovated the theater. Here it's a round earth, prefabricated round earth structural building of 3 floors high. And here it's poured earth, so concrete, like concrete, but without cement. If I have 2 minutes, I show you the work that we have done on this earth. So to say, can we deflocculate the earth, the excavation material, so that we can make it as a concrete? I mean, as a poured material that we can pour into a formwork and then remove the formwork and be able to have a stiff material that can, where we can remove it, that work like a normal concrete material, let's say. And this is now a startup called Oxara, who's promoting this, let's say, cement-free concrete at the end, because it looks like a concrete is just earth. And so to conclude, it is, I think, typically possible to build these climate neutral and circular buildings with the technology that we have, with the material that we have, without waiting for a magical solution like a carbon capture and storage that will, at best, arrive too late, and at worst, not arrive. And for that, we have to think the structure. It's not concrete against anything of concrete, but we can use very low carbon concrete and fast carbonating. Of course, you can use steel, also engineered bamboo. Then you have the floor, like here, it's a reused steel, and then on top, it's a poured earth floor. So you can use such material, like a zero carbon material, and then you compensate the remaining emissions that you had by storing as much as possible carbon in your facades. So typically through straw bale facade or equivalent. And the things that I didn't talk about, but I think Luc was mentioning, is like these technical systems. It is a problem if we really want to go to climate neutral. We also have to think about how do we remove the technical systems, and basically working with hygroscopic material like earth, straw bale, or hemp allows to regulate much more the moisture, which reduce the need of technical systems, and so which reduce also then the embodied emission related with these technical systems. And with that, I want to thank you very much for your attention.
Thank you very much, Guillaume, for a clear presentation. Any questions regarding this presentation from our audience or panelists? I see one question. Thank you for providing useful material. What is the obstacles in using wood materials such as bamboo in tall building structures in order to reduce embodied emissions?
Bamboo, we should make a very clear difference. You have bamboo that you use as bamboo pole, and you do bamboo structure, and there you have connections. You can still do tall structure, but you would not go for high rise. And then you have engineered bamboo, where you just flatten the bamboo and then glue, and then it's like glue laminated timber. So it's exactly the same as a timber. So you could build high rise timber. You have a question of mass, but there's no limitation. And the big difference is that bamboo is available in the place where you actually want to build compared to timber construction. I don't want to say that you should not use timber, but I think there is a huge potential for engineered, so let's say glue laminated bamboo structure for 5-7 story high buildings.
Thank you, Guillaume. There's one other question from Dr. Hu. Thank you for talk on circular buildings. I am curious to know whether you have done a study on the height limitation on rammed earth buildings. It seems like a great alternative to concrete.
Yeah, I mean, again, it depends how we see the problem. So I haven't done structural study. What I know is that to could answer easily to say, first, how high we need to have our cities. And I think this is, at least from a European perspective, 7-story high of dense European cities, it's probably it's the densest cities we have in Europe. So if we go higher, we are actually reducing the density. So if we want to have dense city, 7-story is a very nice height. And then in this case, you have in the city center of Lyon, for instance, 5-story high rammed earth building, like vernacular buildings. So I don't see the problem of going 5-7 stories. The only problem is the thickness of the wall. It's like if you want to do structural rammed earth, you will end up with relatively thick walls, which from a real estate perspective means that you're losing. So this is this is the only question, is how much do we allow, let's say, as the city planner's perspective, to allow to put more on the streets, basically, to avoid the losses of internal space. But not, yeah, I don't know if I answered your question, but I don't think this is not the technical problem, I think.
So there's one question from Luke, and unfortunately the panelists are not able to use the Q&A, so feel free to also unmute yourself if you're a panelist and have a question to ask. So Luke is asking, I like the idea of using building materials to be thermal mass of both moisture and sensitive heat. Any examples on that?
There is an interesting concept that I don't know how much you will transform in other climates, but that works very well in, let's say, Swiss, Austrian context, which is called the concept, the 2226, promoted by an architect called Baumschlag-Eberle, where they have extremely massive wall with insulation. So it's, unfortunately, it's brick, but you could think it as a straw bale structure. But the idea is to have mass, and inside there is absolutely no technical system. There's no technical system except the windows that open automatically if the CO2 level, so the quality of the air, is not good enough. And because of the mass, you don't lose too much your internal thermal heat. And because of your wall that is regulating your moisture, the ventilation that is just made by the window just needs to be there to regulate the quality of the air, so the CO2 and not the moisture. So I think this, if it could be somehow an example, I think this is this is the example where you have mass and you regulate your moisture with your material. And so you just need to care about your CO2 concentration in your room, which then in terms of ventilation requires much less than the moisture.
Thank you very much. Alice is asking, it would be wonderful if the Transform exhibition could travel around for architecture students to see it. Are there any plans for this?
It's more an internal question, but I can answer. But I could ask because I was not involved in the exhibition. I mean, or yeah, just for the Port Earth wall. But I can ask where they have it. But it's because it's a building now that they have built, which really they have these reused windows, straw bale facade, and kind of at the end it's a reused steel structure. But I asked definitely.
Thank you very much.
Thank you.
Yes, indeed. So there are other questions as well, but we have to proceed, and I invite you, Guillaume, to answer the questions through Q&A if you wanted. So our next speaker is Dr. Bernardino D'Amico from Edinburgh Napier University.
Hi, Razam. Hi, everyone.
Hello. Are you able to share your screen?
Not yet.
Oh, sorry, let me make you co-host.
Thank you. Okay. Share. Yeah. Okay.
Very good.
Thank you, Rahman, for introducing me, and of course for inviting me to this symposium. So I will be my talk. This is a joint work with Professor Francesco Pomponi, as Dr. Robert mentioned before. So for this symposium, we decided to somehow take a step back from our day-to-day research, in a sense, and try to look at things a bit outside the box. As you can see from the title, we decided to have a look inside this the realm of carbon offsets. Carbon offsets are currently used for everything, including the built environment. And so we wanted to look at this a bit closely and try to understand whether it's an effective mechanism or is more in general, as we might be brought to think, just a greenwashing mechanism. Anyway, I would like to start the presentation with this graph that I'm sure you all know in the audience, showing the global carbon emission levels over the last 200 years, effectively since the Industrial Revolution. And so we can visualize the speed at which we must achieve net zero emissions by 2050. That's basically the red line we can see there, in order, of course, to have a 50% chance of limiting our global warming between below 1.5 degrees. But at the same time, we also know that we are expected to have an additional 2 billion people living on this planet, according to current estimates. And as a result, we can expect that global demand for additional floor area will keep increasing accordingly. That means that, in fact, it will mean that both total energy used for buildings, for operational use of buildings, as well as demand for construction will, and related supply chain will keep rising as a consequence. I want to show you, for instance, these graphs. The one on the left is showing global production of two main construction materials, of course, cement and steel. And we can see that their demand has been increasing exponentially. Annual production of cement, the binder in concrete, has gone from roughly 0.1 billion tons in the 1920s to 1.6 billion by the end of the century. That is a 16-fold increase in production. Now we are producing about 4.1 billion tons annually. So we doubled production of cement in the last 20 years. A similar story, of course, for steel. So as you can see, the graph on the right side is showing annual extraction rates of iron ore. Iron ore is, of course, the raw material used to make virgin steel. That has kept increasing as well. This despite, as we know very well, despite the fact that steel is indeed a fully recyclable materials, yet we still keep mining more and more of the raw materials. And the reason why I've chosen those two construction materials is because, of course, the production for both of them accounts for roughly 9% of global emissions of greenhouse gases. And we can also see from this pie chart that these kind of emissions linked to the manufacturing of those two construction materials, these are difficult to eliminate, and that's mainly because in addition to the high energy input required to produce those materials, of course, we also have emissions that are released directly from the chemical reactions involved in the manufacturing processes. So, for instance, 60% of carbon emissions for producing cement are coming from calcination of limestone. Whereas for steel, what we have is that cooking coal is used as an additive in the steel making process to reduce iron oxide in the blast furnaces, and that alone, so without accounting for the carbon emission linked to the energy, just for the making of steel, we have that a ton of steel production is roughly responsible for between 1.6 and 3.1 tons of carbon, of direct, so to speak, carbon emissions. What can we do about that? Of course, there is a lot that can be done. The first and main thing is going to be indeed about using less of these materials, try to use less stuff. If we want to achieve, a decarbonized built environment by 2050. After that, of course, we should get on a diet, to paraphrase Dr. Robert. We should use more bio-based material. But at the bottom, at the end, there is still a problem. We cannot likely get to a net zero built environment unless relying eventually partially on carbon offsettings. So carbon offsettings will likely remain unnecessary requirements in order to balancing out these hard to decarbonize materials in the short to medium term. We know that the World Green Building Council, the RIPA, and many other institutions, they do contemplate the use of carbon offsets in order to achieve net zero in buildings. The ISTRUCT, the Institution of Structural Engineering, the UK Institution of Structural Engineers, for instance, they have released a guide recently explaining effectively how to use, how to offset greenhouse gas emissions, and effectively deeming them as a necessary requirement until and unless we can produce alternative materials, alternative products that can substitute entirely carbon intense materials like steel and concrete on all ranges of applications at scale. I think these are two important keywords, because as we've seen in the previous presentation, we know that we can replace in many circumstances these kind of materials. Nonetheless, we do not have a perfect alternative that matches effectively the mechanical and durability and you name it characteristics of Portland concrete, for instance. So of course, I also want to be clear that it should be pointed out that although the inclusion of this carbon offsetting mechanism is almost in every guide and declaration and commitment covering large parts of the built environment professional spectrums, all these guides, of course, they are very clear in pointing out that priority should be given to other carbon reduction strategies, and carbon offsets should be seen as a secondary, albeit necessary option. So yeah, there is clearly a clear trend suggesting that such instruments will play a major role in climate policies for decarbonizing the built environment. And it's imperative we make sure that the adoption at scale of this mechanism will indeed correspond to a reduction in greenhouse gas concentration, atmospheric greenhouse gas concentrations. So it's not going to be just a tool for greenwashing and accounting, neutrality accounting only in theory, but without an actual reduction in carbon emissions. Of course, to understand and so to be able to prevent the risk of carbon offset being used as a greenwashing mechanism, we first should quickly understand how a carbon offset works. And from a physical point of view, it's a very simple mechanism. Essentially, the warming-induced effect caused by a certain amount of greenhouse gas emissions is indeed independent from the geographic location where this emission takes place. So if we have an emission increase and an emission decrease of equivalent amount taking place in two different locations on the planet, then we can conclude that their net climate warming effect can be assumed to be zero. A carbon emitting entity, let's say a building or a construction project, can so compensate for its emission by reducing them of equal amount somewhere else. And by doing so, we can assume that the project can claim to be net zero, meaning that no additional carbon was added to the atmosphere as a result of the construction project taking place. However, when the main risk linked to purchasing these offsets is of course making sure that there is a link of causality between the polluting activity, purchasing the carbon credit, and the offsetting activity, selling the credit. This causality link is often called additionality. Namely, an offsetting project is additional if and only if the reduction in greenhouse gases would have not had occurred had the offsetting project not been financed by the carbon credit scheme. The problem is that verifying whether an emission reduction project is truly additional, it's effectively about proving that it wouldn't have existed without the polluting activity financing the offset in the first place. And so while proving additionality beyond any reasonable doubt is simply not possible, because that would require one to be able to either travel back in time or jumping into some sort of parallel universe where the offsetting scheme was never financed. It's effectively impossible, but in practice we rely on feasibility studies. So we effectively estimate rather than proving whether a carbon reduction project would have been able to go ahead without the offset financing scheme. In essence, verifying additionality, it's a tricky business. But we want to show you in the following slide that there is an even bigger risk that when dealing with these carbon offsets. First of all, we should differentiate between two types of carbon offsetting schemes, namely carbon removal and carbon avoidance. As the term suggests, in carbon removal offsets, the credit is issued to finance a project or an activity that drew greenhouse gas out of the atmosphere. And of course, that could be in the form of afforestation projects or carbon capture and storage, and similia. Whereas carbon avoidance offsets, on the other hand, the credit goes to finance projects or activity that prevent emission from being released into the atmosphere. There is no removal. It's about the aim is avoiding emission taking place in the first place, and project, of course, they can be in the form of preservation of existing forests, implementation of renewable energy generation in order to reduce generation of fossil fuel, or energy efficiency measures in order to reduce the use of fossil fuel. And we could argue that both activities, both type of offsets of removing as well as avoiding carbon emissions, they have both a positive impact on reducing greenhouse gas emissions, which is indeed true. However, what we want to highlight here is effectively that there is a theoretical flaw when relying on carbon avoidance offsets as a part of a net zero strategy. So this is effectively the main subject of this presentation. So let's quickly compare two offsetting projects, namely a carbon removal project, which is about, let's say, planting trees, the one on the left side of the table, and a carbon avoidance project, which is about, indeed, preventing an existing forest to be logged. To figure out the net benefits of both offsetting schemes, the first thing we do, of course, we need to first define a baseline scenario to measure against. And to do so, we assume, I think this is a very important detail, we assume that although we cannot prove it, we assume that there is a very high likelihood that both offset schemes are indeed additional. Namely, no trees would have been planted and trees would definitely be logged had the two offsetting project not been financed. As a result, no change in greenhouse gas atmospheric concentration would take place for the carbon removal baseline, whereas an increase in greenhouse gas concentration would occur in the carbon avoidance baseline scenario. Similarly, we have that trees are being planted and no tree is being logged, respectively, as the two offsetting projects go ahead. As a result of which, a reduction in greenhouse gas concentrations is expected from the carbon removal offset, whereas no change in greenhouse gas concentrations occurs thanks to the carbon avoidance offset going ahead. So we can now measure, indeed, the outcome for both offsetting schemes against their corresponding baselines, and we can see in both cases that we have a net reduction in atmospheric greenhouse gas concentrations thanks to the offsetting projects. In other words, but of course, at the same time, we can also see that there is an upward shift of the baseline for the carbon avoidance offset. In other words, while the carbon removal offsets is reducing GHG concentration from current levels to lowest one, the carbon avoidance offset is reducing greenhouse gas concentration from potentially higher levels to current one. Therefore, it follows by simple logic that when a carbon avoidance project is issued to balance out the emission from a building or project or any other carbon emitting activity, the net effect of both the offset and the building project is indeed a net increase in atmospheric greenhouse gas concentrations. Whereas if a removal offset is used instead, the net increase indeed in atmospheric greenhouse gas concentration is truly null. Despite this obvious fact, we have that carbon avoidance projects are indeed used to offset emissions linked to buildings, construction, and real estate portfolios, for instance. Therefore, these are enabling net zero claim to be made about these activities in spite of such simple logic. And of course, one may argue, wait a moment. Using carbon avoidance offsets is better than using no offsets at all. Of course, that's absolutely true. Because if you are not using offsets at all, then you have a twofold increase in emissions. This is certainly true. This is certainly a valid point. We cannot dismiss, but at the same time, we should also not dismiss the fundamental difference between avoiding avoidance and removal when doing carbon accounting, because if we treat them equally, effectively we can achieve net zero while we have an increase in we can achieve a net zero claim to be made. We enable net zero claim to be made while at the same time we are having an increase in greenhouse gas emissions. So we could end up basically to the paradoxical result of having a net zero built environment where all new construction or refurbishments, you name it, is entirely offset by carbon avoidance offsetting schemes, and at the same time we have greenhouse gas concentrations increasing. So to conclude, carbon offsetting schemes are, and of course their trading markets are now booming as instruments to tackle the climate crisis. These kind of instruments are used for almost everything and anywhere. It's not just something restricted to the built environment. And you know, recent figures, as you can see, they show that almost 100 million tons of carbon offset that were purchased in 2020. Only 5% of these were aimed at financing removal projects. The bulk of it was mainly about avoided deforestation, renewable energy projects, and energy efficiency projects. Now, you may be thinking that I'm suggesting we should stop going and pushing towards renewable energy project and energy efficiency project. That's certainly that is not what I'm trying to say. I do believe that, of course, you know, preserving existing forests, decarbonizing our energy grids, and improving the energy efficiency of our buildings, these are all things that are extremely important and are necessary to fight the climate crisis. And we must do more of this. However, what I'm trying to point out is that if we bargain these actions in exchange for carbon credits as a right to pollute somewhere else, we're really not going to lower greenhouse gas concentrations from current levels. We're just simply going to shift the baseline levels against which we are measuring all reductions. Thank you very much, and happy to answer any question.
Thank you very much, Bernardino. We have 2 minutes left for the questions, if there is any question from our audience or panelists. Alice, please.
Hi, thanks very much, Bernardino. I was just wondering if you have the scenario, which I believe does happen, where some bad person logs a forest, cuts down virgin forest, and then grows new trees to get the carbon offsetting. So I recognise that this isn't what is meant to be happening, but to stop that happening, you need to have regulation, and you need to have surveying, and you need to have site visits to quite an extensive scale. I was just wondering if you looked at what the carbon implications of that would be.
Yes, I agree with you. I think I personally don't even believe, to be honest with you, that the solution is going to be planting more trees or using carbon capture and storage technologies. The point, I would say, the presentation was about demonstrating that carbon avoidance are theoretically flawed as a system for offsetting emissions. Carbon removals may be theoretically sound, but likely practically flawed as a solution. So we should really, I guess, keep offsetting as the last resort. We should definitely try to avoid. So in this sense, avoidance is good if we avoid emissions in the first place, rather than using them as an excuse to emit somewhere else, or you know, to shift emissions geographically or over time.
Absolutely agree. Yeah. Thank you.
Bruno has a question. Bruno, please.
Yes, thank you. Good afternoon. I think we need both construction materials and energy. So I think we should expand the system. If you just plant trees, you will have to produce standard electricity, for instance, and you will emit also CO2. Whereas if you use renewables, you will avoid that. So if you expand the system, then you don't have so much difference between avoided and offset, I think.
Yeah, absolutely. As I said in during the presentation, we definitely need, obviously that's a no-brainer that we need to decarbonize our energy grid. But if we assume that 1 kilowatt hour of one additional kilowatt hour of energy produced in a renewable way will automatically correspond to 1 kilowatt hour less of energy worldwide being produced using fossil fuel. That's not something really we can, it's proved. Most of the time we have a rebound. We effectively end up just using more energy. So, which is why I don't think financing renewable energy via offsetting scheme is the right way to go to reduce carbon emissions. Of course, we know that fossil fuel is a finite resource, and eventually we will run out of it. But yeah, that's obviously going to be too late. But we need to get this done by 2050. So.
Okay, thank you very much. Because of the time restrictions, we have to move on to the next presentation. But there is one more question for you to answer, Bernardino, in the Q&A. It would be great if you could answer that. Our next speakers are Dr. Matan Meyer, Assistant Professor of Architecture at IE University, and Dr. Jonathan Greenham, Assistant Professor at Harvard, presenting their work on characterization of links between embodied carbon and thermal mass. Jonathan and Matan, floor is yours.
Thank you very much, Rahman. I believe that Jonathan is sharing the screen. Okay, good. Yeah, let me see. I don't seem to have control. Like I don't see where it is. So I'll just ask you to flip the slides if that's okay, Jonathan. Okay. So thank you very much, Rahman. Thanks for organizing this event, and thanks for inviting us. Jonathan, can you go to the next slide?
Yeah. Okay.
Yeah. Okay. So our presentation today pretty much follows the structure of the chapter. We'll start with a brief introduction. We'll talk a little bit about prior work in the field that we're looking at. We'll describe the method. We'll show some results. Then we'll discuss the results, and we will finish with future research. Next, please. Okay, so the general motivation of the study is quite similar to the motivation of this whole symposium. Over the last 3 decades or so, we've seen a shift in the balance, in the energy balance or the carbon balance, in the life cycle perspective in buildings. You can see on the left-hand side a study from '96 that shows the embodied energy as roughly 10% of the overall life cycle of a building, and on the right you see a study that was done 20 years later that shows a completely opposite situation. So the share of embodied energy or embodied carbon by extension as part of the life cycle of a building has increased over time. Next one, please. And that increase can be attributed in part or in most to increased efficiency, either efficiency of mechanical systems, efficiency of lighting systems, efficiency of plug loads. but basically increased efficiency of machines. Next slide, please. So in order to achieve even deeper reduction of operational energy, passive means is something that designers and engineers have at their disposal, and that could be high performance insulation materials, that could be thermal mass, that could be other means. Can you go to the next slide? Okay, so in order to discuss those passive means, let's look at the life cycle net zero carbon scenario. In that kind of scenario, the contribution of these passive means is more pronounced. So in a life cycle net zero carbon scenario, you would use on-site renewables in order to compensate for both the embodied carbon that you're consuming and also the operational carbon that you're consuming. Next slide, please. So in this scenario, if we look at thermal mass, for example, thermal mass would help us to reduce that operational burden. Next slide, please. But depending on what kind of thermal mass we use, what kind of material we use for thermal mass, for thermal storage, that reduction in operational energy might result in a higher increase in embodied energy. So, for example, if we think of concrete as kind of a classic thermal mass material, concrete is very carbon intensive. So using concrete might help us to reduce the operational carbon of the building, but would increase the embodied carbon significantly. Can you go to the next slide? And that will also obviously will require us to use more on-site renewables in order to offset that carbon. And then we're going into this kind of almost like a feedback loop where we need more on-site renewables. In order to harvest more on-site renewables, we need more equipment like PV panels, etc., which adds more embodied energy to the tally. This is a kind of a loop that is very difficult to get out of. Next slide, please. So as you can see, there's a kind of a delicate balance here between the benefits that thermal mass can provide in terms of carbon reduction and the embodied carbon cost of thermal mass. And it depends very much on which materials you're using. So that kind of dilemma was what we were aiming for when we conducted this study and we wrote the chapter. Next slide, please. So really the research question that we're looking at here is what are the trade-offs between thermal mass performance and embodied carbon emissions? Next slide, please. So looking at prior work very briefly. So one publication that we found very inspiring, and we use this kind of the foundation for our study, was this publication from 1980, Passive Solar Design Handbook. The interesting thing about this publication is that it really ties this idea of carbon storage to the amount of material used. So as you can see here on the graph on the left, it surveys 5 different material groups and basically shows the thermal storage capacity of these materials depending on the thickness of the walls that are used in. So that allows one to make a pretty direct connection or direct correlation between thermal mass or heat storage capacity and carbon emissions, embodied carbon emissions. Next slide, please. So our method is really based on that kind of understanding, and the workflow that we used here was to choose several material groups as kind of a starting point. Then to look at the embodied carbon data for these materials out there. We looked at 3 different sources that are kind of widely used sources. And then in parallel to that, also to calculate the thermal mass performance of those materials in a specific configuration. Those 2 sets of data in tandem allowed us to reach carbon emissions trade-off for these range of materials in this specific situation. And after we calculate these trade-offs, we could start looking at the limitations of the system. So we looked at limitations in terms of design, system, and data, and we'll discuss all of these in the next few minutes. Next slide, please. So looking at the carbon, so as I mentioned, we looked at 3 different sources of data here. The first one was Gabi in Tally by extension. The second one was Circular Ecology, which is the ICE database that's based on the BAT inventory. And the third one was Granta, ANSYS Granta. Now, as you can see on the right, the right is a mapping of the data that we found for 15 different material groups. So we looked at 15 kind of basic material groups of construction materials. And as you can see, there's a wide range of results for each one of these materials. Next slide, please. So here you can see that range for these 15 materials groups. You can see that the highest range, like the longest bars, are in the natural materials, solid and engineered timber, for example. And then on the right-hand side, in materials that are more speculative materials like polymers or ceramics, those had a wide range of results in terms of carbon data for the same sets of materials. This is an account, a more detailed account of that variation, and you can see those horizontal black bold lines were the averages that we eventually used for our modeling in this study. Now Jonathan will keep talking about the thermal mass properties. Go ahead.
Yep, thanks, Matan. So similarly, we looked at what was available for the performance in terms of the diffusivity of these materials. But of course, in this case, we're just limited to the ANSYS Granta database because of the typical kind of embodied carbon databases don't carry material performance. And in this case, if we're looking at diffusivity, we're looking at a number that has this kind of Goldilocks situation where we want something that is quick and something conductive and dense, but not too conductive to become a thermal bridge and not too slow and to become an insulator. So we can start to look across that same selection of materials and see that there's a wide variety, but for the most part, we're looking for a larger diffusivity. And if we zoom in a bit, what we start to see is that what we'd expect is that our concretes and our kind of natural stone materials and earth materials have the highest conductivities and densities. Therefore, the diffusivity is high and in that optimal range. But we do also see things like thermoplastics creeping into that optimal range as well. And I'll just note that things like natural materials start to have a really wide range of performance across the data set that we're looking at. And so as a quick kind of overview, just to get us on the same page, when we're thinking about thermal mass performance, we can look at this diagram and assume that if we had a kind of thermally insufficient wall, we might assume that the inside and outside temperatures could fundamentally be the same if we had a nearly transparent building. When we start to bring in thermal mass into the situation, we're doing one of two things. The energy it takes, the vibration of these molecules to warm up that material, means that we're storing some amount of energy in the selected material. And the first thing that does is start to actually shape the peak temperature. So we have energy reductions in that space, and therefore we might have less thermal load to manage using some type of system. And then the other aspect of thermal mass that's beneficial is that we're going to store that energy throughout the day and then release it later, shifting when that peak energy is actually hitting the grid for cooling. And so going back to the model that Matan introduced, I won't get into all the details, but we take a lot of this model to actually show how the performance of these materials work using a diurnal heat capacity model. So we're basically saying over a 24-hour period of time, how much energy would be stored by 1 square meter of this material with variable depth. And then we can start to apply different functionalities such as the kind of absorption of the material, the amount of kind of daylight fraction the material might have. Is it just solely connected through convection, and other kind of design criteria using this existing model. Our addition to it, which I'll get into, is just simply looking at how do we start to convert that into carbon, and then comparing that back to the initial embodied carbon for that material. So if we take a closer look at the existing model, we can look at something like an isolated concrete wall in a space that's just linked to the rest of the building through convection. And we can see here kind of where we have this optimal range. And the model also shows, if we look at the x-axis, this is the depth of the wall, and then the amount of storage on the y-axis, we actually see some diminishing return. So at some point, you just have too massive of a wall. It can no longer store more energy than it's being kind of affected over that 24-hour period. And so we see a diminishing return at some point. The model then can be expanded to look at kind of an interior partition where it's loaded from one side, and maybe we have direct radiant gain along with convection on the surface. And then the model can also be applied to a situation where we have a double loaded wall, either as an interior partition or exterior partition. And we start to see this kind of increase in the ability to store heat throughout the day. So instead, this heat storage is over a period of time of 24 hours. And so fundamentally what we're doing is saying how much heat can we store in a simple functional unit of 1 by 1 square meters of this material with a variable depth. We're not accounting for the rest of the building construction. And then we're counting how much embodied carbon goes into making that functional unit. And fundamentally, how much operational carbon is avoided in terms of the systems that may have been in place and the source energy and carbon emissions to then thermally control that building. And so we take that curve that I showed in the previous model, and what we're adding to it is an understanding of how much kilograms per square meter are going into the operation of that in terms of an offset, in this case, the avoided aspect of using thermal mass. So we take this diurnal heat capacity from the model, we look at how many degree days where we have an actual temperature change between the surface of the thermal mass and its environment throughout the year. We estimate the service life, so we use a long service life of about 60 years. And then we look at the carbon intensity of the grid, where that alternative energy might be coming from. And in this case, we use kind of an extrapolated number for a linear decarbonization from current US average to 2050. And then we have this kind of optional aspect of what would the equivalent COP of an HVAC system be, which Matan will get into. And what we're able to do is then say, okay, how much embodied carbon based off the global warming potential of that particular material are we having per the depth of this material? So what is the total volume when we start to incorporate the depth of the material, and we start to overlay these over that same kind of period of time. And what we start to say is that we have these kind of 3 different conditions, where in the black, we see that there's actually some type of carbon offset, this avoided carbon that is not being emitted at the grid side, or the burning of fossil fuels at a boiler or similar. And then we have these other areas where we have a net zero, where it all balances out. And then we also have an area where the mass could actually be too thermally massive. We actually are putting too much mass into the building, and it's ineffective in its performance. And so in the study, we do this across a number of different materials. And what we see is somewhat what we would expect from intuition. We see that masonry, earth, stone, and concrete all start to have this capacity to offset in terms of their initial embodied carbon. But when we get into things like glass and polymers, that goes away very quickly because of the high embodied carbon. And then there's an interesting conversation around timber being somewhat thermally massive, and whether or not we're going to virtualize its emissions later on down the line, or are we going to count them as negative, or actually account for those emissions past the growth cycle of the biogenic carbon storage of the timber. So I'll hand it back to you.
I think I might be able to control the slides now. Yeah,
great.
It looks like I can, right? Okay, I know that we're short on time, so I'll do this section very briefly. So in this discussion, we wanted to talk a little bit about the limitations of that method and the model that we developed. And I'll talk about 3 different types of limitations. One would be design limitations, the other one would be system, and the third one would be data. So when we look at the design impact, now it doesn't seem to do it.
Yeah.
Okay, yeah, just go to the next slide, please. Sorry about that. So in terms of design impact, if we look at the findings that we just shared with you, where we have this offset line, if we that offset line really refers to only one specific situation in terms of how that thermal mass is configured in terms of geometry, where it's positioned in terms of exposure to solar gains, etc. So if we add to that to this graph all these other kind of uncertainties in terms of how do we actually employ that thermal mass, you can see that we have a wide range of solutions here, and in some of these solutions, this material is found to be feasible at specific thicknesses, and in some instances, it's found to be not feasible at all. So that shows you that design has many uncertainties here in terms of how do you actually implement the thermal mass and the results that you get out of that. Next slide, please. In terms of system impact, there are two notions that come into consideration here. One is the coefficient of performance, that is basically how efficient are the heat pumps or the mechanical system that you're using. And the other one is the energy mix that you're using, whether the energy mix involves dirty energy sources or clean energy sources. Next slide, please. So again, in the system impact, if we look at this kind of singular result that we reached, and then we add to that the influence of the grid, the dirty grid versus the clean grid, you can see that there's a wide range of possible solutions here. And then if we add to that, can you go to the next slide? Yeah. So if we add to that to the coefficients of the efficiency of the mechanical systems here, you can see that adds even more, even a wider range of solutions here. So again, this comes to show that there are uncertainties that really depend on the system that we're looking at and the context that we're operating in. Next slide, please. And to just illustrate this specific point, if you look at two European countries, Denmark and Poland, at 2030, if you look at the grids of these two countries, if we were to implement this study in Denmark, where you have a projected 14 grams of CO2 per kilowatt hours, versus Poland, where you have 566 grams of CO2 per kilowatt hours, we would get very different results. Like in the case of Denmark, using concrete as thermal mass would probably be environmentally prohibitive because the grid is very clean, while in Poland, using concrete as thermal mass would be completely feasible or beneficial environmentally because the grid relies on coal, etc. Next slide, please. And lastly, the data impact. So as we mentioned before, there's a huge variety of data sources that are out there, and the data sources that we looked at displayed a range of different results for both embodied carbon and for thermal diffusivity. So if you look at both of these variables in concert, again, you get a variety of possible solutions. So more uncertainties that play a role here. Next slide, please. And then lastly, the idea of estimated service life also plays a major role here. Usually in studies, one would assume a 60-year estimated service life, while in reality, in certain contexts, that estimated service life could be 30 years, especially if we talk about contexts in the US or for sure in Asia. Buildings tend to have actual shorter lifespans, so that would add even greater uncertainty to the results that we showed. Next slide, please. So that brings us to the last slide of future work. So because of all these uncertainties and because of all these variations, we're thinking as a next step to expand this study and to actually model these different parameters and these different types of scenarios. And where we're at now, we're looking at around 31,500 different models that we're trying to run and to show the complete variety of solutions for this relationship between thermal mass and carbon footprint. Next one, please. Yeah, that's the last slide. Just acknowledging our research assistant and the Harvard Center for Green Buildings and Cities. Thank you.
Thank you very much.